In this video we'll talk about electrophilic aromatic substitution with substituents. So if you already have something on the benzene ring, that can direct where the electrophile goes. Activators generally direct to the ortho position, so this is ortho, and para position, so these are going to be called ortho-para directors. Things that are deactivating, which are pulling electrons out of the ring, generally direct to the meta position, so these are going to be called meta directors, as we're going to see. So we'll talk about things that direct ortho-para positions, what's an activating and a deactivating group, resonance versus induction, and things like that in this video. Okay, so when I mean substituents, what do I mean? So let's say we take methylbenzene, right, and we just think theoretically, how many products could form? Well, what's going to happen, remember, what's going to happen if you mix together nitric acid and sulfuric acid is you're going to generate the NO2 plus electrophile. And it could go here, and those two things would be ortho to one another, or it could go here, and those two things would be meta to one another, or it could go here. Those two things would be para. If we went here, it would be the same as this meta product, and if it went here, it would be the same as this ortho product. So we have three possible products. We can have ortho-nitrotoluene, or we can have meta-nitrotoluene, or we can have para-nitrotoluene. So this is called meta, and this one is the para product. So which one forms? Well, actually there's two major products in this reaction. If we look on the next slide here, we see that when we run this reaction, the major product is the ortho product and the para product. And so we call methyl an ortho-para director, meaning that it directs electrophilic aromatic substitution to the ortho position and to the para position, and not very much to the meta position, so we're going to ignore this very small amount of product that forms. And the major products of this reaction are the ortho product and the para product. So let's talk about why. Why would methyl be an ortho-para director? And this is the rationale is important to understand. So if we look at the reaction mechanism, which is going to tell us why, we start with toluene or methylbenzene, right? And when we mix together nitric acid and sulfuric acid, we generate this electrophile, the NO2 plus electrophile. So let's look at what happens in each case, right? If we make the ortho product, the first step, remember, is we get this sigma complex. We have a positive charge here, right? And this has two other resonance structures that would place a positive charge on this carbon and on this carbon. If methylbenzene were to attack the nitronium ion to give the meta product, right, this double bond could attack, right? And if we attach the nitro group to the meta carbon, now we get a positive charge here, and a double bond here, and a double bond here, and then two other resonance structures that we'll talk about in a second. And in the last case, let's imagine attacking the nitronium ion. The same double bond, except now we're going to put the nitro group in the para position, okay, so let's evaluate just these three resonance structures. Which one do you think would be the most stable? Well, this one is tertiary, and this one is secondary, and this one is secondary. So this one looks pretty stable since it's tertiary, and the two other resonance structures, which I'm not going to draw but we'll talk about in class, are both secondary, right? But if we draw the resonance structure of this, we put a positive charge here and a positive charge here, so we have two other secondary resonance structures. So when in the meta case, we don't have any tertiary resonance structures. In the in the ortho case, we have one tertiary resonance structure, and if we draw the resonance structure here, we get a tertiary carbocation. And so notice that when we attack at the para position and at the ortho position, we generate a tertiary carbocation resonance structure, but when we attack at the meta position, we don't. And so the transition state leading to the attack at the meta position is going to be higher in energy, which means that it's going to happen slower, and thus the major products are attack at the ortho and the para position. Let me show you what I'm talking about. Okay, so if we attack at the ortho position, right, we get this very nice, stable tertiary intermediate. A resonance structure leading to that intermediate is low in energy. So the activation energy is small, and this reaction happens relatively fast, right? But we can't generate a tertiary resonance structure in this case, right? So the energy of this carbocation is higher, the activation energy is higher, so this is slower. This activation energy is small because, again, we have this tertiary carbocation, so this happens relatively fast. So then our major products are para and ortho because of the stability of the carbocations that lead eventually to those products. Any alkyl group, methyl, ethyl, propyl, is going to help you form this tertiary carbocation. So all alkyl groups, we're going to consider those ortho-para directors because the transition states from the ortho and para attack are lower in energy, and thus those products form faster. Okay, let's look at other substituents. What happens if you have an oxygen, an ether, for example? Okay, so we could at least think about this in two possible ways, right? An oxygen atom could be pulling electrons out, right? Oxygen is electronegative, it might be pulling electrons away, but the oxygen, we also have resonance structures that place a negative charge at the ortho and the para positions. So in the resonance hybrid here, right, we have a partial negative at each one of those ortho and para positions, and it turns out that electron donation by resonance strongly trumps induction, right? And since we're attacking an electrophile, these ortho and the para positions are activated towards nucleophilic attack because we have a partial negative in the resonance hybrid of this compound, and thus when we run the reaction, what we see is a strong preference for ortho-nitroanisole, para-nitroanisole, without really any meta product being produced. So ether groups, things that contain lone pairs that are directly bonded to the aromatic ring, will always have resonance structures that place partial negatives at the ortho-para position, and thus they're ortho-para directors. And they're also strongly activating, which just means that they react faster than benzene. Okay, so to really understand fundamentally what's going on, we have to look at the mechanism again, and instead of going through all the resonance structures, what I want to just point out here is that this is very similar to the case that we just looked at with toluene, right? If we have, for nitrating, and we attack the nitro group, right, we're going to form a tertiary carbocation, but it has the additional stability associated with one additional resonance structure, right? We can form another resonance structure because now oxygen can donate electrons by resonance. So we get this resonance structure, which is really nice. If we remember our rules for resonance structures from first semester organic chemistry, this has all full octets. So this is strongly contributing to the overall resonance hybrid. This is a very stable resonance structure, and this can happen in the case of ortho attack, or para attack can lead to that same resonance structure. Which we can draw essentially like this. To get us this same resonance structure, except with the nitro group, the para position. But no matter how hard we try, if we attack at the meta position, we can never get this resonance structure, which has all atoms with full octets. So again, because of that, the meta has a more unstable intermediate or carbocation, and thus reacts slower, and so we don't observe as much meta product when we have electron donating substituents by resonance, like an oxygen atom. Okay, so let's talk about deactivated groups. So methyl group and any alkyl group is going to be activating, and it's going to direct to the ortho and the para position. Anything with a lone pair of electrons, like an oxygen or a nitrogen that can donate electrons through resonance, is also going to be activating the benzene ring, as we saw, and is going to direct to the ortho and the para position. So what happens when we have a nitro group? Well, what we have is the situation, right, where we can put a positive charge, a resonance structure with a positive charge at the ortho and the para position in this ortho position. So notice now our resonance hybrid, right, has partial positive charges at the ortho and the para position. So these positions are deactivated, meaning that ortho and para positions react slower, right, because there's a partial positive that's going to repel that incoming electrophile. It's also, nitrogen atom is also electron withdrawing by induction, so we have nitro is called an electron withdrawing group because it's pulling electrons out by resonance and by induction. And so the benzene ring is going to be deactivated. It's not going to want to react with an electrophile. So electron withdrawing groups are deactivating, meaning they react very slowly. Let's see what product we get from a nitrobenzene undergoing electrophilic aromatic substitution reaction. So let's say we nitrate benzene. Notice now we have to heat the reaction to 100 degrees. That's because this compound is deactivated. It reacts slowly, so we need to speed up the reaction by heating it. And notice that we don't get very much ortho or para product. By far the major product is the meta product. Well, that's because these positions were deactivated, whereas the meta position was not deactivated, and thus reaction happens virtually exclusively at the meta position. Nitro groups and other electron withdrawing groups are meta directors. Okay, so just to clarify here, we can think about this from a resonance perspective and look at the ortho and the para positions being deactivated. We can also look at what would happen to the intermediate if we attack an NO2 plus, right? What are we going to get? Well, we're going to get a carbocation which is bonded to an electron withdrawing group. What's going to happen? Well, we're going to be pulling electrons away from this carbocation, so this is destabilized. Even though in the past when we had a tertiary carbocation it was stable, we're pulling electrons away from something that's already positively charged. That's a destabilizing interaction. If we do the same thing and we look at meta attack, remember we're never going to put a positive charge on this carbon. So no matter what we do, when we attack at the meta position, we're never destabilizing. We have a positive charge here, which is going to also, by resonance, go to these three carbons, but we're never going to put it on this carbon, right? It's never going to be destabilized, and thus meta is lowest in energy. And that one forms fastest, as we'll see in the next slide. So what are the trends that we've observed so far? Well, things that are electron donating like alkyl groups, like a methyl group or an OCH3, these things are pushing electrons into the ring and activating the ortho and the para positions. These are called ortho-para directors. Things that are pulling electrons out of the ring by resonance, like a nitro, group, that's going to be a meta director. So far the activating groups that we've seen are ortho-para directors. Activating groups react faster than benzene, so these two groups react fast. The nitro groups react slow, and we call that deactivated. We call these activated. So the activating groups that we've seen so far are ortho-para directors. The deactivating groups that we've seen so far are meta directors. Let's see if that trend always holds. Of course, there's always exceptions to the rules that we introduce in organic chemistry. And halogens, in this case, are going to be the exception. So let's say we have chlorobenzene. Well, we could expect several different outcomes, right? Chlorine also has lone pairs of electrons that it can use to generate resonance structures that put a negative charge at the ortho-para position. So we could imagine that the ortho-para positions are activated through resonance. But remember, halogens are strongly electron withdrawing. So what happens is both of these trends are important. Because halogens are electron withdrawing, that means that the ring is deactivated, which just means that it reacts slower than benzene or something that didn't have a substituent on it. But it's also an ortho-para director because those ortho and para positions have this partial negative charge, which makes them react more quickly with an electrophile. So if we nitrate chlorobenzene with nitric acid and sulfuric acid, the major products that we'll expect will be ortho and para nitrochlorobenzene, but no meta. So this is an ortho-para director, and that's because the lone pairs of electrons on the chlorine can stabilize a positive charge at this carbon. So for example, let's say that we drew, just for the sake of time here, I'll just draw attack at the ortho carbon with an electrophile like the nitronium ion, right? We get this carbocation, and just like the case before when we had an oxygen there, now we can draw a resonance structure that is very important, right? Because now all the atoms have full octets, so the fact that chlorine is electron donating through resonance is very important, and that's really basically what explains why it directs to the ortho position and the para position. Okay, so to summarize, we're basically talking about two types of directing groups. You can have an ortho-para director, or you can have a meta director. For ortho-para directors, they usually have electron donating groups. They can always stabilize a carbocation intermediate. That can be an alkyl group that can donate electrons through induction, or you can have a lone pair of electrons on that atom that can donate electrons through resonance, right? All ortho-para directors are activated, which means they react faster than benzene, except for the halogens, which react slower than benzene but are still ortho-para directors. And in class, we'll talk about strong, moderate, and weak activating groups. Meta directors are always electron withdrawing, and they're always deactivating. And I want you to, in class, we'll talk about strongly and weakly deactivating groups.